Auzubillahi minash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Oladimeji T.A., the SS2 physics teacher of CTY Model College, Ibadan, Nigeria. Hello students. You are welcome to week 7 of our e-learning class for third term 2019-2020 academic session. And the topic of discussion for this week is going to be refraction of light waves. Refraction of light waves. And under this topic, we are going to consider the following subtopics. 1. Refraction of light through rectangular glass block. 2. Refraction of light through triangular glass prism. 3. Effect of refraction. And lastly, we are going to consider critical angle and total internal reflection. So let us start by considering the first subtopic, refraction of light through rectangular glass block. What is refraction? It is noticed that when light travels from one medium to another medium of different density, its direction and speed change as it enters the second medium. The change in speed and direction of the light ray as it travels from one medium to another is what we call refraction. And this change in direction is brought about by the change in speed because the media are of different density. So refraction is a change in the direction and speed of light rays as the rays travel through two media of different densities. So when light rays travel from here to glass, its direction and speed will change because glass is thicker than air. Also, when light rays travel from here to water, its direction and speed will also change because air and water are of different densities. The diagram below shows an example of a ray that travels from here to glass. Let's study the diagram. You can see from the diagram, A-hole represents the incident ray, which is coming from the air, and it enters the glass. So medium 1 is air, while medium 2 is the glass. We can see that the direction of the ray changes as it enters the glass. The ray is refracted towards the normal because it is traveling from an optically dense medium to an optically denser medium. So A-hole is the incident ray, while hole B is the refracted ray. And the normal is a line perpendicular to the surface. The I represent the angle of incidence, which is the angle the incident ray makes with the normal, while R represents the angle of refraction, which is the angle the refracted ray makes with the normal. So this is a typical example of refraction for a ray that is traveling from an optically dense medium to an optically denser medium, that is from here to glass. So let's move to laws of refraction. There are two laws of refraction. The first one states that the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. Then the second one states that the ratio of the sine of angle of incidence to the sine of angle of refraction is constant for a given pair of media, that is sine I over sine R is equal to constant. To explain these two laws, let's go back to our diagram. Now look at the diagram. The first law states that the incident ray, the normal, and the refracted ray at the point of incidence all lie in the same plane. As you can see from the diagram, look at the incident ray, the normal, and the refracted ray. They are all in the same plane, the vertical plane. So the law holds, that is, all the three are in the same plane at the point of incidence. Now let's look at the second law, which states that for two given media, the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant. What that one is saying is that for a particular angle of incidence and the corresponding angle of refraction, if we find the sine of angle of incidence and this is divided by the sine of angle of refraction, we are going to get a particular value. Now, if the angle of incidence is now increased or decreased, and we also obtain the corresponding value of angle of refraction, and we find the ratio of the sine of angle of incidence to the sine of angle of refraction again, we are also going to get a value which is almost equal to the value we got. If we continue increasing or decreasing the angle of incidence to get the corresponding values of angle of refraction, and we proceed by finding the sine of angle of incidence to the sine of angle of refraction, we will always get a constant value. And that is what that law is telling us, that the ratio of the sine of angle of incidence to the sine of angle of refraction is always equal to a constant. So, and this second law of refraction is also known as Snell's law of refraction. We shall come to that later. Now, let's proceed by looking at refractive index. What is refractive index? Refractive index is always denoted with letter N. And this simply represents a measure of degree of refraction offered by a medium. That is, it's a way of measuring the refracting power of a medium when light rays pass from here to the medium, and it is obtained by calculating the velocity of light in here divided by the velocity of light in the medium. For example, if a light ray passes from here to glass, the refractive index of glass with respect to here, which is denoted as shown in the equation, is given by the velocity of light in here divided by the velocity of light in glass. Refractive index has no unit. Refractive index can also be calculated by finding the sine of angle of incidence in the here and divide it by the sine of angle of incidence, sine of angle of refraction in the medium. So refractive index is also given by the ratio of sine I to sine R. Note, the refractive index of the hair with respect to glass for a ray traveling from glass to hair is given by the reciprocal of the refractive index of glass with respect to hair. What they are saying here is that, when we want to calculate the refractive index of glass with respect to hair, we made a ray of light to travel from here to the glass, and we find the velocity of light in here over velocity of light in glass to give us the refractive index of glass with respect to hair. Or we find the ratio of the sine of angle of incidence in the hair to the sine of angle of refraction in the glass to give us the refractive index. So, as if Now the ray is traveling from the glass to here, that is the other way around, and we want to calculate the refractive index of A with respect to glass. We just need to find the reciprocal of the refractive index of glass with respect to A as shown in the equation. Refractive index can also be given in terms of wavelength of light. So the refractive index in terms of wavelength is given by the wavelength of light in the first medium to the wavelength of light in the second medium. That is, if the light is traveling from here to glass, I want to find the refractive index of glass with respect to here. We just need to find the wavelength of light in here divided by the wavelength of light in the medium. Effect of refraction. Refraction of light can be used to explain a number of phenomena such as 1. Mirage, 2. Apparent depth of a swimming pool, 3. Bending of a straight object, e.g. a straw, when immersed partially in a bowl of water. So we shall look at all these effects later in the course of the topic. So another way of expressing refractive index is by using real and apparent depth. What are real and apparent depth? You can observe, if you look down through a swimming pool, the depth appear shallower, and the real depth of the swimming pool is deeper than what you are seeing. So the real depth is the real depth of the swimming pool, but the depth that appears to you that you are seeing is what we call the apparent depth. So the refractive index of water in the swimming pool can be calculated by dividing the real depth by the apparent depth. So that is another way of expressing refractive index, that is real depth over apparent depth. There's another word known as apparent displacement. So what is apparent displacement? If you subtract the apparent depth from the real depth, you have what we call the apparent displacement. And apparent displacement is denoted with letter D and is given by R minus A, where R stands for real depth and A stands for apparent depth. From the formula that refractive index is equal to real depth over apparent depth, if you make apparent depth the subject of the formula, you have real depth over refractive index, which is denoted as A is equal to R over N. So substituting for A in the formula for apparent displacement, R minus A, so we have apparent displacement D is equal to R into bracket 1 minus 1 over N, where N is the refractive index. Now let's consider some examples to see how we can apply what we've learned so far. Example 1. A fish appeared to be 2 meters above the surface of a pond when viewed directly from above. How far below the surface of the pond is the fish? Refractive index of water is given. In this question, we just need to understand what we are looking for. A fish appeared to be 2 meters below the surface of the pond. 2 meters there is the apparent depth. Then we are required to find the real depth of the pond, given the refractive index of water. So we just need to apply the formula that refractive index is equal to real depth over apparent depth. So making the real depth the subject of the formula, we are going to have real depth is equal to refractive index multiplied by apparent depth. So when this is done, our answer is going to be 2.66 meters, which is the real depth of the pond, which appear to be 2 meters. Let's look at example 2. The wavelength of red light in here is 7 times 10 raised to the power minus 7 meters. What is its wavelength in a glass of refractive index 1.5? B. What is the speed in the glass? The speed of light in here is given as 3 times 10 raised to power 8 meter per second. Solution. The wavelength of red light is given as lambda is equal to 7 times 10 raised to power minus 7. That's wavelength in here. Wavelength in glass is unknown. That's what we are looking for. Refractive index is given as 1.5. If you remember the formula of refractive index in terms of wavelength, refractive index is equal to wavelength of light in here divided by the wavelength of light in glass. So let's apply this. Substituting for all this value, we have refractive index is equal to 7 times 10 raised to power minus 7 over lambda g, where lambda g is the wavelength in glass. So making lambda g the subject of the formula, we have 7 times 10 raised to power minus 7 over 1.5, which is going to give us 4.7 times 10 raised to power minus 7 meter, which is the wavelength in glass. Let's go to question B. In terms of velocity, refractive index is given by velocity of light in here over velocity of light in glass. Velocity of light in here is given as 3 times 10 raised to power 8 meter per second. And velocity of light in glass is what we are looking for. Substituting this, 1.5 is equal to 3 times 10 raised to power 8 divided by Vg, where Vg stands for the speed of light in glass. So making this Vg the subject of the formula, we are going to have Vg is equal to 2 times 10 raised to power 8 meter per second, which is the speed of light in the glass. Example 3. An object is placed directly below a glass block of thickness 3 cm. Calculate the lateral displacement of the object if the refractive index of the glass is 1.5. Here, the real thickness of the glass is the real depth. Then, refractive index is given. They want us to find the lateral displacement, which is apparent displacement. Remember, the formula for apparent displacement in terms of real and apparent depth is D is equal to R into 1 minus 1 over N, where N is the refractive index and R is the real depth. Substituting this, we have D is equal to R into N minus 1 over N. So 3 is equal to 1.5 minus 1 all over 1.5. And this will eventually give us 1.0 centimeter, which is the apparent displacement. Another way of doing this, you can apply the formula R is equal to real depth over apparent depth and get the apparent depth first. Once you have gotten your apparent depth, then apparent displacement you are looking for will now be real depth minus apparent depth. And that will give you the same value as D. Example 4. A ray of light strikes the surface of glass at an angle of incidence 60 degrees. Find the angle of refraction in the glass, given that the refractive index of glass is 1.5. Here, the angle of incidence is given as 60 degrees. Refractive index is given, so we have to find the angle of refraction. We just need to apply the formula for refractive index in terms of angle of incidence and angle of refraction, and that is N is equal to sin I over sin R, where N is the refractive index, I is the angle of incidence, and R is the angle of refraction. Substituting the values we know and make R the subject of the formula, we are going to have R to be 35.5 degrees, which is going to be the angle of refraction. So this is where we are going to end the first period for this week 7. Until the second period, when I will come your way again, My name is Oladimeji T.A., the SS2 physics teacher of CTY Model College, Ibadan, Oyo State, Nigeria. Until then, remain blessed and stay safe. Assalamu alaikum wa rahmatullahi wa barakatuh.